once again for coming along for our ecological discussions this evening. Today we're going to look at an issue of primary concern nowadays, and that is abrupt change. Abrupt change in both natural systems and ecosystems. We're beginning to realize that some of the abrupt changes that occur in ecosystems provoke abrupt changes in social, political, and economic systems, and it should be the other way around. In other words, the abrupt changes in ecosystem should be absorbed by stable political systems, not amplified by or aggravated by those political systems. So we're going to look at the ways in which, in effect, scenarios and syndromes work out in long-term history. Abrupt collapse in natural systems and in human history. We're beginning to realize that the natural ecosystem is a lot more variable than we thought, and that it varies not over only gradual evolutionary time, but sometimes quite quickly because of natural processes that are interrelated and trigger one another in an amplifying manner. Now, social systems that are too closely focused on a particular natural regime can find themselves disturbed very quickly if those systems change abruptly. And that's what we want to look at today. Syndromes and scenarios. There are regular syndromes in ecosystems. Syndromes of warming and cooling, for example, ice ages that come and go. But sometimes they come a lot faster or go a lot faster than we were accustomed to thinking before. And the geologists have now developed the means of looking at this on a year-by-year, decade-by-decade basis. The new techniques that they've evolved to look at ice cores in the Antarctic and in Greenland have enabled them to resolve the annual precipitation in these areas. The carbon captured in the bubbles of CO2 indicates the annual CO2 concentration in the atmosphere. And they can resolve things now to a much more refined extent than only 20 years ago when they started this research. And those syndromes are becoming more and more apparent. These are being laid out in a series of lectures in what is known as the AGU, the American Geological Union, Geophysical Union actually, and they hold an annual meeting in December. And it's in that meeting that you get a presentation of a lot of papers, including this important one, which won a prize this year for its importance, called Abrupt Climate Change, Past, Present, and Future. And he discusses at length what's meant by abrupt climate change. Let's take a look.
So now let's talk about some abrupt climate changes. I'll start with the past. Abrupt change is a common and natural feature of the Earth's climate system. When I was a graduate student, I learned about, as I said, Milankovitch, etc., the gradual kind of climate change forced primarily by the Sun-Earth interaction. When I started to work in this area, we started to recognize it was Greenland ice cores, ocean sediments. I remember wonderful talks about abrupt change, even in, for example, the snails living in the Thames River mud. But at the time, people said, yeah, climate can't really change that fast, right? So I'm going to show you data from a few ice cores here, so we'll actually do some science in this talk. Mostly from the summit cores and then North Grip and Neem. So we're going across something in the neighborhood of 5-6 degrees of latitude here. This is the view we have now of climate from a Greenland ice core. In green is the, I believe, North Grip temperature record. It's stable isotopes translated into temperature, but we've also measured all of these changes in other ways, so we know these are temperature changes. But this is a very angry climate, if you will.
Okay, now a very angry climate is one that's on a graph sort of changing very abruptly, very fast, right? In a short period of time, big swings. And he goes on to illustrate this very powerfully in a series of other kinds of statements. And as he indicates, the story of abrupt climate change is far more abrupt and far more severe than we ever thought. Take a look at his data here.
So we do know that these things are real. We've seen them now in many, many ice cores. And what we're beginning to find out now is that what we mean by abrupt is, in other words, how abrupt is an interesting question. As I pointed out, we put 20 years for that deuterium excess change in the Di-3 ice core. The Di-3 ice core is not shown here, but we have North Grip, Gist2, and Neem all plotted on top of each other. We can actually see annual layers in here, so we know when the annuals are. And these are markers, volcanic markers, that we use to cross-date the core. So we're not matching the isotopic records up in this case. We're using the volcanic markers and then counting years in between to line these three records up. And you can see that across a fairly large area, this is deuterium excess, there's a very systematic excess shift and a lot of common variance throughout this system. So there's very large signal that's going on here. In this case, we think it's the retreat of sea ice. And now we know that this is a matter of 1 to 2 years. So in a matter of 1 to 2 years, there was a very large change in what happened out over the ocean. As I said, the only thing we can think of that happens that fast is a change in the sea ice extents. And that's happening, and it's not just a question of human lifetimes, it's not just a question of decades. It's, as I tell my students now, it's less time than it takes to get through college, right?
It's a matter of 1 or 2 years. It's less time than it takes to get through college. You can have huge switches in climate. We're worried here in Boston when it snows a bit, right? And we're saying, oh, it's an anomaly, it won't happen every year. Well, maybe we got to pay attention to what the geologists are saying at the AGU. It's pretty extraordinary when you look at it.
Which almost gets their attention. If I could bring this down to the amount of time it takes to get to Thursday, which is the new Friday, then I would point out here that recent breakthroughs over the last 5 years or so in analytical systems now allow us to pull these ice cores out, put a stick of ice on a melter, and continuously measure isotopes. All of these were cut laboriously in a cold room somewhere and put on the mass spectrometer. We can now measure these things continuously, and we can measure them rapidly. We could do 5 or 6 ice cores across a transition for something like this in a matter of a couple of days. So the technology is changing, and look for more and more and more high-frequency data out of the ice coring community in the next several AGUs.
Okay, the next several meetings of the AGU, American Geophysical Union, you will hear more and more of this kind of information. Why? Well, because the science has gotten better and better, the techniques for analyzing these cores. They're going to have more and more reinforcing cores and be able to address this question of how abrupt is abrupt.
The other point I noted here was that, so it's not just deuterium excess, but I noted that the deuterium, which is a proxy for temperature, changed in about a human lifetime. Well, this is not my best slide for this, I apologize, but we now have, again, with the matching up the volcanic events, we can now show that what we thought was a human lifetime is probably made up of 2 events. So there was a warming, a plateau for about 30 years, 40 years, and then a warming again. Such that out of that 10 degrees of warming, it was about 1 degree per year for 5 years. Then it plateaued for about 40 years, and then it went up about 1 degree per year for another 5 years. So a very different view is emerging now. These abrupt events actually have abrupt events lurking within inside them. This is beginning, I think, to give us the ability to understand what really controls these things. But I would point out to you that 1 degree per year for 5 years is 100 times faster than the current warming. We've had about a degree, maybe a little bit more than a degree, over the last 100 years. And we've noticed that. Imagine something that was even 100 times faster than that. This would very clearly, 1 degree per year would be something you would absolutely notice. And it's happened many times in Earth's history.
1 degree per year has happened many times in the Earth system. In fact, it really gets worse, as he says. Take a look.
we've now, when we first pulled out the North Grip ice core, we noticed that this is the bowling warming now, which is about 14,000 years ago, showing another very large warming, about 10 to 15 degrees C. This, in the North Grip ice core, was about 1 year, 1 to 2 years in the isotopic record. We underplayed it, we talked about it, and I believe it might even be mentioned in the North Grip paper, but we didn't stress it because, again, we were going, how can this possibly be? It wasn't until we got the NEAM ice core, which shows the same thing, and again, these cores are matched up not by matching up the jump, but by matching up by independently dating these things. But we now know that in northern Greenland, this is not true for southern Greenland, but in northern Greenland, there must have been some threshold in which the atmospheric circulation got to some point and then bam, it changed, such that you got about a 10-degree change in mean annual temperature in northern Greenland happening in about 1 to 2 years. And we now have replicated that in 2 ice cores. That's 1,000 times faster than the current warming. So this is clearly something that would get all of our attention.
Clearly something that would get all of our attention. Well, that's kind of an understatement. I mean, this is unbelievable. What's happening now is pretty extraordinary, but he's saying that it was 1,000 times faster in the past.
I would point out that abrupt change is not just something that occurred in the past. This is, as we were writing the report and as we were talking about the report in public, something that as a scientist I didn't really think about and didn't really consider and didn't really appreciate, to be quite honest, is the fact that abrupt change is happening now. That if we were to go 200 years out in the future and look into the record of today, we would see abrupt change. And those abrupt changes would be just as clear as the abrupt changes that I talked to you about that we see 10, 15, 20,000 years ago in ice cores. Right? There are many such abrupt changes, but let me focus on one of them. Arctic sea ice. I would also point out that groundwater loss is an abrupt change that's happening today, and it's something you very much should keep your eyes on, including many of them, species extinction, ocean acidification, etc. But let me talk about Arctic sea ice. Right? So Arctic sea ice, since the 1970s or so, has decreased by roughly 50%. This is the average monthly sea ice extent in September from the fine folks across the parking lot from me at NSIDC. By any measure, that's an abrupt climate change. In less than a human lifetime, Arctic sea ice has shrunk tremendously, shrunk noticeably, shrunk significantly. You pick your adjective, right? Certainly faster than anticipated. The experts who've been looking at this, who've been modeling this, who've been predicting this is faster than what they thought. This has many impacts on Arctic ecosystems. It has changed shipping routes. It has changed tourism. It has changed coastal erosion. If you are living in Alaska, you know about climate change. It is a reality. It's something in your face. It's something that maybe we don't see down here at 30, 40 degrees north as much, but in the Arctic, this is a very real change, and it's happening, and it's an abrupt change. So when your friends and neighbors, when you talk to them about climate change and you happen to mention abrupt change, you go, oh, was that something that just happened in the past in ice cores? No. It's something that's happening today.
Okay, it sure is, but it is also something that has happened in the past, and it's worth looking at when. Now, the archaeologists are beginning to look at why ancient civilizations fell, as they say, in the past. Why ancient Egypt fell. Well, it turns out there was a huge climate change component to it. Looks like a desiccation, a drying out of the old kingdom in Egypt. Let's take a look.
Archaeologists believe they have evidence that the sudden collapse of the kingdom of ancient Egypt was due to a catastrophic drought. During the same period, another ancient empire was also in turmoil. The Akkadian Empire extended far across Mesopotamia, now part of Iraq and Syria. The agricultural capital was Leilan. The ancient city was surrounded by fertile tracts of land and had a population of 30,000, according to Yale University archaeologist Dr. Harvey Weiss.
When I first went to Leilan, I was terribly impressed by its physical size. This was really a very, very large city. The same way that Kansas City served as the hub which collected grain from the great grain belt of the United States. So Ceylan served as a great collection point for northern Mesopotamian agricultural production.
Okay, northern Mesopotamian agricultural production, in effect, according to Harvey Weiss, is what was crucial in this region, and what started to emerge was a huge drought in this area that first affected agriculture, and then with agriculture, everything else that followed. Take a look.
But everywhere he dug in the once thriving city, Weiss discovered the same mystery. A layer of wind-blown sand similar to the one Hassan had found in the lake by the pyramids.
Wind-blown deposits of different sized grains. Sandy deposit. Very, 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 very fine. This deposit represents something on the order of 100 or 200 years of extremely different climatic conditions.
For over 100 years, there were no signs of human habitation, or any life at all in the sediments.
There was, even within this dust, an absence of earthworm. And so this was becoming a very perplexing situation.
It seemed that Ceylan had quickly turned from a bustling city into a ghost town. The collapse of Ceylan appeared to coincide with the fall of the entire Akkadian Empire. Weiss began to suspect the same cause that Hassan had identified for the collapse of the Old Kingdom of Egypt.
We initially thought drought, arid event, aridification. And then we began to see that this was rather extensive, that it extended across regions. It extended into Turkey. It extended into Palestine. There was a drought period in Egypt. There was a similar abandonment collapse situation on the Greek mainland.
There's increasing evidence to suggest that the collapse of the Old Kingdom was not unique. Around 2200 BC, half a dozen highly advanced civilizations simultaneously came to an abrupt end. Weiss suspected only one thing could have had such a widespread and profound effect: a dramatic change in climate. But like Parkak and Hassan in Egypt, he needed conclusive evidence. An expert in ancient climates may provide the answers Weiss was looking for. At the Lamont Doherty Earth Observatory in New York, paleoclimatologist Dr. Peter Domenical searches for ancient climate change events.
Wow.
At his disposal is the world's largest drill core archive. It's an extensive geological record of climate change. When Weiss contacted the observatory, Domenical was surprised by Weiss's suggestion of such a fundamental climatic change.
My initial response was, this is incredible. What first struck me as a paleoclimatologist was, why didn't I know about it? Because there we see there was this proposed climate change that wasn't something that we were familiar with.
Okay, now this is actually very interesting because it's a new kind of evidence. This isn't sea cores, but sediment cores, taking cores from the bottoms of the oceans. And sure enough, when they go looking for it, they find it. Now, others have been worried about scenarios about climate, and a fellow named Peter Schwartz outlined one for the military not long ago, indicating that abrupt climate change like this would bring about a kind of severe convergence of crises, especially in arid areas. And the scenario was taken up by them and looked at in detail. Take a look.
Now we go to a place where it is not hard to imagine desperate nations going to war over a scarcity of environmental resources like water caused by climate change, as our own Jim Maceda reports in our series of reports we're calling The Perfect Storm. It's a scenario a lot of people are preparing for already, just in case.
African peacekeepers face off with angry villagers. It's only a military exercise conducted by U.S. forces in the Horn of Africa. But this could be the future, the aftermath of an environmental disaster.
That is floods. That is huge famine problems because they all result in movement of people.
Triggered by a new kind of enemy, climate change. So serious a threat that former CENTCOM Commander General Anthony Zinni co-wrote a report on global warming as the future spark for conflict.
Could cause tremendous humanitarian problems that the local government's not able to cope with or deal with, could result in peacekeeping, peace enforcement requirements.
Already, the Pentagon and NATO have factored in dozens of climate hotspots in the shaping of future missions.
We're trying to establish where we may think that will happen, how it will manifest itself, and what action we can do to try and prevent that.
Okay, and what do they look at? Well, they look at Egypt in particular. Because Egypt is very subject to two things: aridification, the diminishment of water flowing down the Nile, and sea level rise, the intrusion of salt from rising seas in the Mediterranean and the whole agricultural plain around Alexandria. So the military is starting to plan for this, and in fact there's a clear indication in the reports that they produce for themselves, national security and the threat of climate change, that climate change is on the agenda. Further, climate scientists have been pointing out the relationship between the drought in the Middle East currently and the rise of ISIS. This is making things very clear. It's no longer subtle that there's a link. Abrupt collapse in natural systems and human history has been a long-standing phenomena, but we haven't been able to link them up before the detailed history from the American Geophysical Union, starting to emerge about abrupt climate change, the detailed history of ancient archaeology, the detailed information now emerging about ancient droughts that led to the collapse of ancient civilizations in the work of people like Dr. Harvey Weiss down at Yale. All of this is starting to emerge with a very clear indication that this is now part of a larger movement towards transition studies. We need transition studies because we're in the midst of a transition.